So, as Jean just said, this is part of a collaboration which I believe is now 8 years old between the Collège de France and University of British Columbia, but this is the first time that physicists have been involved. It was actually a biology initiative in the beginning. And so I'm going to talk about something which is, I think, of interest to a lot of people here. But it's going to be from a point of view which is not that of somebody from quantum optics, because I'm not from quantum optics. On the other hand, I will be, one of my purposes for coming here is to actually learn more about quantum optics. So apparently there's a problem with the server in the college right now, which means that I've put the notes for this course at this online address initially. But they will become available on the site of the college at some point. I'm not sure when. Anyway, I had an email from the person responsible in the college saying that there was still a problem with the server. Okay, so this is the plan of the course. The way I've designed this is that there's a lot of formal material for people who want to look at it. But you don't have to. The formal material, a lot of it is on the web page. So the emphasis during the course, if you like, when I actually talk, I'm going to be mostly addressing myself towards people with an experimental background, or at least not intensively theoretical. On the other hand, for those who want to look at the notes, they're more addressed to theoreticians. So you have your choice. The first talk will be today, and in fact will be the most theoretical of the 4 lectures. So the lectures, this is not the way you're supposed to do it. You're supposed to start easy and get hard. This course is the other way around. It starts more formal and then becomes less so. In each one of the lectures, I'm going to be discussing one example, which I'm calling a real-world example. In other words, it'll be talking about some real phenomenon, real experiment. And then for the rest of the time, I'll be discussing, background material. So my first lecture will be mostly about formal matters, and I'm going to be laying a strong emphasis throughout this course on path integral formulation of things, because it's much more geometric and visually intuitive, and therefore one can learn a lot from it. I'm actually going to start by talking about something that Alain Aspect talked about last week. In fact, this is supposed to be a response to what he was saying. He's not here, of course, but that's how I'm going to start. In the second lecture, I'm going to be, and in fact, in the second and the third lectures, I'm going to be talking about what I call a spin net. Now, that'll be a network of 2-level systems. So it could be anything from a quantum icing system in 1 dimension, or 2 or 3, or indeed in as many as you like. But it could actually be something as simple as a single qubit, but would be coupled to its surroundings. And we'll be looking at different aspects of this. And in particular, the big focus in the lectures will be on decoherence phenomena, which is of considerable interest, but it turns out there's much more to decoherence than you might think. And in fact, I'll be discussing kinds of decoherence that are not usually addressed, in fact, which don't necessarily involve coupling to an environment. All of this is, if you like, some mixture of condensed matter and quantum optics. The final lecture will be about recent work that I've been doing, which is, I guess, in the field of quantum gravity. It concerns the question of whether or not one can, using experiments in a lab, attempt to understand the current conflict between quantum mechanics and general relativity. I will say a little bit about quantum gravity, but not too much, because I suspect that most people here don't have much of an interest in it, but enough so that you get a flavor of what's going on. But the real point of this lecture will be to discuss a possible experiment, an optomechanical experiment, to try and test these ideas. So that's the plan of the course. So, as I said, in the notes, you'll find a lot of theory, but I'm going to try and be fairly geometric in my approach when I actually speak. So, this is my response to Alain Spey from last week. He asked, what is the essence of quantum mechanics? Actually, he said, what is the mystery of quantum mechanics? And in that, he was referring to an old phrase of Feynman. This goes back to his lectures on physics. And he said the fundamental mystery of quantum mechanics is contained in the two-slit experiment. And we all know what this is about. We pass some object, and it's allowed to pass through two different slits. And Feynman analyzed this using path integrals. And he basically pointed out that this can be understood by looking at the two possible paths that the particle can take. And we sum, in wave function language, we simply sum over these alternatives. And then the probability that the particle arrives here is given by the square of this amplitude. And of course, we get this interference term. And it's very interesting that if you only pass a very small number of particles or photons through, then you just see a random set of arrivals on the screen of photons or particles. But of course, if you pass a lot of them through, then you see this interference pattern. And the way that Feynman described this was using path integrals. And the way we think about this is that the amplitude for the particle to start at Q prime and end up at Q is given by the sum over all possible paths between these 2 points. So that's what this symbol means. We sum over all possible paths here with a weighting factor. And that weighting factor is just e to the I times a phase. And that phase is the classical action divided by h bar. And this is very well, of course, known. It's already discussed in the Feynman lectures on physics, which were written for undergraduates. And what's really nice about it, well, there are a number of things that are nice about this, which I'll discuss. But here you see that it very well captures the non-local character of quantum mechanics. But it was a long time before people realized that actually the Feynman formulation is not the same as the Schrödinger formulation. The first article that I know of which really says this clearly is by Cécile Moret de Witt. This was in 1972. You probably know that she and Laidlaw invented the idea of fractional statistics in 1977. And in fact, she was relying on this insight. So she says here, Feynman's formalism gives directly an unambiguous answer to global problems. Other formalisms use ad hoc extraneous conditions to deal with global problems, such as boundary conditions on wave functions, symmetry or anti-symmetry properties of the wave function, and so on. And this is the key point, their answers are not necessarily identical with Feynman's. So Moret de Witt actually spent many decades developing certain aspects of the path integral formulation. She was essentially a mathematical physicist. Curiously, some of you may know, the name de Witt comes from the fact she was married to Bryce de Witt, who was a pioneer of quantum gravity, and who used some of these insights. And this is an example of what she means. This is the amplitude to go from one place to another, which in a two-dimensional system has to be divided into a sum over different topological classes. And this is what led to the idea of fractional statistics. It's actually rather clumsy to try and write this using wave functions. Oh, sorry, I've got this thing here. And what I want to point out was that when you formulate indistinguishability in path integral language, you immediately come to formulas like this, where you see that because you have this sum over different topological classes, only certain statistics are allowed, which depend on the dimensionality. So this is something that has to be imposed ad hoc when you use a wave function analysis, or you usually derive it by asking about the properties of the probabilities when you exchange particles, but that doesn't work in 2 dimensions. But there are other aspects, as Alain pointed out. Another important one is the property of entanglement. Now, he was actually not correct in saying that Feynman didn't realize this until 20 years later, because you already find his discussion of this in the book by Feynman and Hibbs in 1965. where we see that you can understand the idea of entanglement by summing over amplitudes for pairs of particles. And this is, in fact, precisely the diagram that Anna showed, but you'll find it in Feynman and Hibbs. And this is also a consequence of superposition for multi-particle systems. In other words, entanglement is not something different from superposition. It's simply what happens when you superpose wave functions for more than one particle. Now, there are two other essential things which I think are somewhat mysterious in quantum mechanics, which were not mentioned. One of these is the spin statistics theorem. Why is it that there is an association between spin and statistics? And it turns out you can't explain that in non-relativistic quantum mechanics. You can only explain it by going to relativistic quantum field theory, as was first shown by Pauli in 1949. And in fact, nobody has found an explanation simpler than that. Berry thought he had about 20 years ago, but it turned out to be incorrect. And Feynman himself regarded this as a challenge. He said, I have never been able to find a simple explanation of this result, which means I don't understand it. You'll find this in a book that he wrote on QED, which is a summary of lectures that he gave in New Zealand about 30 years ago. And so this is actually an outstanding problem in physics. How do we give a simple explanation of the spin statistics theorem? And finally, the most mysterious problem of all in quantum mechanics, which I certainly don't think anyone knows the answer to, is how is it we proceed from probabilities to concrete results in quantum physics? Now, usually people talk about decoherence when this problem is raised, and we'll discuss that. But the idea is that whether we're talking about density matrices or wave functions, we end up by writing results of measurements as definite results. And this, of course, this is a picture reproduced from the book of Franck Laloy, his book on quantum mechanics, which was published a couple of years ago, called Do We Really Understand Quantum Mechanics? And I think the answer he would like to give is no. And of course, the problem arises particularly when the states that one is looking at are macroscopic in some sense. I should say in parenthesis here that although it is argued that we have macroscopic superpositions now in some experiments, there's severe disagreement about this. And in fact, I personally think that the arguments of people like Birgitta Worley to the effect that the superpositions are still very much mesoscopic are correct. I may have time to talk about that. So this idea of superposing macroscopic states has not actually yet been produced in the lab. Okay, now this is an example of what I mean when I say that I'm going to be discussing things geometrically, but for those who are interested in the mathematics, it will be on the screen and in the notes. So I just want to say a little bit about the path integrals. I remember when I was here last year, somebody remarked to me in a fairly testy way, nous ne faisons pas ça ici, meaning path integrals. So I would like to remark that actually there's a very nice tutorial article on path integrals written by Cohen Tenergy, which you will find in Journal de Physique about, well, nearly 20 years ago. So it's actually not true. The old formulation of path integrals relates it to the simple propagator of the kind that's really just another way of writing the Schrödinger equation. So we say, well, the amplitude for a particle between two different times in non-relativistic quantum mechanics, so this is an operator here, is just the exponential of I over h bar times the Hamiltonian. And this function here simply satisfies what is basically just the Schrödinger equation. This is the Hamiltonian minus h bar dt, and this is a delta function here because we have a step function here. And if we take the eigenfunctions of this operator, then of course we have this well-known formula, which is very useful in experiments because you can write this function here as a sum over amplitudes at different positions divided by this factor. So as I mentioned before, for Moret de Witt, we should be looking at a more general object, which is actually not the same. This is the amplitude to go from x prime to x. Of course, in simple problems, it is the same, but as, for example, we see in 2 dimensions, it may not be. And then more generally, if I'm talking about some field, so this is actually a scalar field, but we could imagine that this was just the photon field. We're actually talking about amplitudes for the field, the whole field, to go from one configuration to another. So this is actually not at all the amplitude to produce a photon here and absorb it here, which is the field expectation values that people typically write in quantum electrodynamics. This would be a correlator between two values of the vector potential at 2 points in space-time. But here we're talking about the entire field throughout space-time changing from one configuration to another. It's a quite different object. And we'll find that it turns out to be a useful object later on. Okay. Now, why would I want to use path integrals when people are much more used to wave functions? Well, we'll see why. One of the reasons is that, as I said before, it captures these topological features of quantum mechanics. It captures the relation between phase and action along world lines, and that's world lines, not worldliness, sorry. And there's a clearer connection to classical theory. But we'll see that when you use path integrals, there's no need for wave functions or operator algebra or canonical field theory, and that turns out to be really useful. And in fact essential when one starts to deal with more complicated theories. And it's fundamentally non-perturbative, which is very important. Okay. Now, for those of you who are not used to path integrals, the first problem you have is, what do we mean by sum over all paths? How do we count them? How do we decide how many paths, what is, in other words, as one says, what is the measure involved in this integration here? And I'm not going to discuss that in detail because I want to keep things reasonably simple. But it is something that comes in and which is discussed in the notes, which you'll find on the website. Now, this is horrible. This slide is horrible. But it actually turns out that the meaning of it is quite simple. So let me explain what all of this means. And it's really important to pay attention to the pictures here rather than the formulas. So what I'm asking here is, okay, we've talked about how a wave function evolves, and we say that we can discuss everything in terms of amplitudes to go from one place to another. But what about a density matrix? After all, we know that in general in quantum mechanics, the system may not be describable by a wave function and will need a density matrix. So how does a density matrix propagate? Well, this is easy to answer if the system is free, if it's not coupled to anything. Then we just have a propagator for the density matrix here. So the density matrix starts off. It has two arguments. So this is my initial density matrix here, this blue thing. And it has two arguments, 1 and 1 prime. And then it propagates, and this is the propagator, these two lines, to this second density matrix here. And so the propagator is just this K0. And the K0 is just the amplitude for these two lines. This is the line going one way, and this is the line going the other way. Why do we have lines going in opposite directions? Well, because remember, the density matrix is the outer product of psi and psi bar. So one is the complex conjugate of the Hermitian conjugate of the other. And so naturally that means there are two paths, and the integral, so the weighting factor here, involves the exponential of I of raised bar times the action going along one path minus the action on the other, because it's going in the opposite direction. Okay, so this is very well known. You might say, well, okay, very interesting, but what happens if my system is interacting with its surroundings, if it's interacting with something else, and if I don't care about that something else? So this might be some particle, like an electron, coupled to photons, and we're not actually observing the photons, we just want to know what the electron does. So we then ask, well, how do we describe that? As I was saying, we now want to know what happens if we're trying to describe the dynamics of the density matrix of, for example, an electron, which is coupled to photons, but we don't want to know about the photons. We have to somehow average over their behavior. And this is where the path integral description is very interesting, because at no point, you notice, have we ever talked about operators or projecting density matrices or anything like that. All we're doing is writing down paths. In fact, a question you often get asked when you're teaching this sort of thing to students is, so when do you quantize? And the answer is you never do. You're always writing down paths and averaging over different paths. And the quantum mechanics appears simply because these exponents here contain h bar. It seems almost miraculous. So the same thing happens here. Now we have an action which involves some system here, which could be an electron, some environment here, which say is photons, and some interaction between them, which of course is in quantum electrodynamics is just the fine structure coupling. And now we want to average over these photons. And of course we can average in different ways. There will be some set of constraints. But without worrying about that, let's just ask what is now the amplitude for the density matrix. Well, it's again given by sum over two paths for, in this case, the electron. And again, we have the weighting factor, the same weighting factor for the two paths of the electron. But there's another weighting factor here. So this is going to emphasize some paths over others. And in fact, we'll see that paths that move too far apart from each other are actually receive less weighting. And this is actually what we call decoherence. You can't pull the paths too far apart. These two paths here can be as far apart as you want if there's no environment, but the moment you have an environment, then this thing here will actually prevent the paths from getting too far apart from each other. Now, formally, this thing here can be described in words. This is a product of unitary operators acting on each one of the environmental modes. So this U of k is just a unitary operator acting on the environmental mode, but it depends on what the system is doing. In other words, this for the QED example, this is unitary operator describing the evolution of each mode of the electromagnetic field, but the time evolution of that mode is conditional on what the electron is doing. If the electron goes this way, the QED modes will do one thing. If the electron goes that way, they'll do something different. In other words, what the photons do depends on what the electron does. And so that's what this weighting factor is telling us. It's telling us that when we average over the photons, then we're averaging over some function which depends on what the electrons are doing. In fact, we can in words say the unitary operator describes the evolution of the kth environmental mode given that the central system follows a path q on its outward voyage and q prime on its return voyage. And then we can write this, and these formulae are very complicated, but you can see what they mean diagrammatically. Now, the electron goes up here and comes back here in the density matrix, but it's interacting with photons. And that may mean what we call here a self-energy correction. The photon is emitted by the electron and then reabsorbed, but it can also involve exchanging the photon between the two lines. Now, I talked about this as though these were photons, but of course they might not be photons. They might be something else. We might be dealing with something like spins, in which case the things look a little bit different, as we'll discuss. This here was more to give you some intuition. The definition of the path integral is discussed in an enormous number of books and review articles, and this is to remind people of what that's all about. So I'm not going to say much about this slide, except to say that you can define the path integral by chopping it into infinitesimal intervals. This is, in fact, again, a picture from Feynman's book in 1965. He imagines taking a path and chopping it into many intervals by just putting screens with slits between the emitting point and the receiving point. And then if you imagine having an arbitrary number of slits here and an arbitrary number of barriers here, cloison tend vers l'infini, then you end up with this path integral. But this is just generalization of ordinary calculus to paths. And this is how Feynman counted paths. Now, actually, when we go to gauge theories or to quantum gravity, we have to be more sophisticated about defining this measure. And if people want to read ahead, these are two nice articles about that. Sorry, 3 articles. Now, these integrals turn out to often be very simple. They're just Gaussian integrals, except when you deal with spins. And there the path integral is more complicated, and I'll discuss that later. It's a famous old problem in path integral theory, how to write down the path integral for spin, which was not solved until the 1980s properly. Okay, so I've been writing down these actions and saying, well, this is what they are, but one thing you learn in physics is that all Hamiltonians or Lagrangians are actually effective. That is to say, they all involve some restriction on the Hilbert space of the system, and they all apply in some energy range. So if you want to see what I mean, I sometimes ask people in philosophy of physics, what's the Hamiltonian of a hydrogen atom? So they'll say, oh, that's really simple. And they'll just write down free particle bouncing around in a box, and you say, but I didn't specify that the energy range was 10 MeV, mega electron volts. Of course, then it looks very different. So it depends on what energy you're at. And so there's this kind of mantra in physics now where you talk about the effective Hamiltonian of a system in some energy range, and that the form of that depends on things like the ultraviolet cutoff. So you can imagine here a set of levels over a large energy range here for a system with some effective Hamiltonian. And we now truncate out all of these high energies, and we're only interested in this low energy system. But of course, the Hamiltonian looks different. And so people talk about, there's all sorts of words that are used here in talking about the way that the Hamiltonian will scale as we change the states and the Hilbert space. We talk about the flow of the coupling constants and fixed points and so on. And in particular, I'll be asking what happens if we start off with some system which has both the dynamics of the system itself and whatever it's coupled to defined over a large energy range. So this is supposed to be a Hilbert space product between the Hilbert spaces of the system and whatever it's coupled to. And then we truncate down to low energies. What's going to happen? And again, I'm not going to discuss the formal theory too much. I'll be trying to give you an intuitive idea of what happens. But this is complicated. So this, for example, would be a superconductor. These are the different interactions involved in a superconductor. This scale here is the energy in degree Kelvin units. So this would be 100,000 Kelvin. In other words, basically 10 electron volts. And this would be 10 to the minus 10 Kelvin, 1/10 of a nanokelvin. And these are the different energies that are involved. This is the Fermi energy and the electron-electron interaction. This is the Debye coupling to phonons. This is the typical superconducting gap energy, condensation energy. But we have all sorts of other things as well. If we're dealing, for example, with a superconducting device, we may have some tunneling energy. This would be a Josephson plasma frequency, and so on. These are nuclear hyperfine couplings in different parts of the superconductor. These are couplings to paramagnetic impurities. These are nuclear hyperfine couplings, and and these are internuclear couplings, and so on. And depending on which energy scale you want to work at and what phenomenon you want to understand, you have to scale out some of these and keep the others. And so your effective Hamiltonian changes as you lower the energy. And of course, this is why the literature is so large in superconductivity, because people are looking at different phenomena at different energy scales. And the same is true, for example, it's even worse if you're in a magnetic solid. I'm not even going to go through all of these different energy scales. And so this is why the literature on magnetic systems is even larger. I'm not going to say anything about this slide unless people want me to talk about the Hubbard model, but sometimes this simple scheme doesn't work so well. And this is because if you truncate to low energies, the Hilbert space can depend on how many particles are in it. So you can transfer particles in and out of the Hilbert space. In the case of the Hubbard model, one imagines that there are two bands separated by an energy, which is the Coulomb repulsion energy, this U. And now, if this is half filled, then the system is supposed to be an insulator. But if we transfer particles in or out of the system, then the Hilbert space can change. the low-energy Hilbert space. And this is what's called the spectral weight transfer problem here. And it has an analog in string theory, which is called ultraviolet infrared mixing, which means that there's a lot of discussion about how one is supposed to write an effective Hamiltonian for the Hubbard model. But this would take me too far away. I just want to mention it to give you an idea that in strongly correlated systems, it's not always obvious how one is supposed to carry out this renormalization. Okay, now let's go to the main theme of the first few lectures here, which is how do we write down an effective model for some system? It could be a cavity in a quantum optics lab, or it could be a superconducting qubit, or it could be some of the other systems I'm going to talk about, for example, the quantum icing system, which can be realized in many different ways. How do we describe this with an effective Hamiltonian? And it turns out that we're going to have to deal with the coupling of this system, whatever it is, to two different kinds of environment. One of them is an environment of oscillators, so-called oscillator bath. First discussed, well, actually at the beginning of quantum mechanics, but in fact you could say that in classical physics it was discussed by Rayleigh in the 1860s. But in his model of friction. But the idea basically is that you couple the central system here to a set of oscillators. These are labeled by Q. And that the couplings to these oscillators are rather small. And in his original papers on this, Feynman explained why these couplings have to be small. He said, imagine that these modes, these environmental modes, are in some box. And of course, they extend through the box. And they're coupled to something in the box. Could be an atom, could be something bigger. But as we make the box bigger, these wave functions have to spread out through the box. And the overlap integral between those wave functions and the object they're coupling to then gets smaller and smaller. In fact, it goes like 1 over square root of the number of modes. And if we then take the number of modes to be large, then the coupling constant squared is going like 1 over the number of modes, which is very small. So these couplings are 1 over root n. And of course, when you then multiply by the number of modes, you get back an answer which is independent of n. And this all looks very much like Fermi's golden rule. And in fact, as Feynman pointed out, you can essentially found quantum field theory for a set of delocalized modes inside this system in this way. But what's very nice in his paper is he said only if these are small. And so this describes environments of phonons or photons or magnons or spinons, whatever, if they're delocalized. Okay? On the other hand, they may not be delocalized. In any real solid, you have lots of modes that are not delocalized. They're actually localized in space. Defects, dislocations. Vibrons are actually sort of like Einstein phonons, localized in space. Localized electrons, spin impurities, nuclear spins, and so on. If you take the purest crystal of copper, you'll find that the concentration of defects and dislocations in it is still roughly 10 to the minus 5, the best prepared samples that one has. So these are always there. And it turns out that they can't be described in this way. They have to be described in a different way, where we imagine, the simplest way is to imagine them as two-level systems. This is, again, an old model. And these two-level systems are described by Pauli matrices, these sigma k. And their Hamiltonian will, in general, have local fields acting on them. These may not be magnetic fields. They could be electric or strain fields. And there may actually be small interactions between them, although because they're localized, those interactions are weak. And then they will be coupled to the central system by some coupling, which may not be small, actually. In fact, often, this coupling is quite big. So, for example, hyperfine interactions to nuclear spins can be as much as half a Kelvin. And that's far larger, typically, certainly than the interactions between the nuclear spins, which are down by 6 orders of magnitude on that, or whatever local fields may be, which will typically be 3 orders of magnitude less than that. So these are two different kinds of bath, if you like. And again, I'm not going to talk too much about the formal theory here, but one can go through various maneuvers to derive these effective Hamiltonians, both for the oscillators, and this was done, for example, by Feynman, or also in this well-known paper of Caldera and Leggett. But you can also, these derivations, as I say, don't work in the case of localized modes. So then for localized modes, you have to do it differently. And again, I'm not going to go through this formal theory now, but I'll just say that when you deal with spins, you have to worry about the fact that we deal with spin path integrals, which are more complicated. Okay, so this is a summary of the formalism, which I'm not going to discuss today because it's kind of messy, but it's for those who are interested in it. But this is telling you what the forms for these influence functionals, these weighting factors, are in the case of the oscillator bath and the spin bath. And this is what one uses to do calculations. Okay, so one of the main things that we're interested in here is decoherence. So let's start by asking what we mean by decoherence. Let's go back again to the two-slit experiment. So we have a particle, or a photon, which is going between these two slits, and with amplitude psi1 and psi2. And now we imagine that this object, say this electron, is coupled to an environment, which could be photons. This is, of course, a very well-known experiment. As I said, Koen-Tanerjee discusses this in his tutorial article. Now, the problem is that we can imagine starting off with an initial state here for the electron, an initial state here for the photons. And as time evolves, we'll end up over here, and we have to now recognize that the amplitude has evolved to a superposition of psi1, that is paths going this way, with the photons having been modified to these phi sub q1, and psi2 for the electron with the photons modified to a different phi 2. And now we ask, well, what happens if we want to calculate the reduced density matrix just for the electron, which is what we observe on the screen? The amplitude that we'll see on the screen here will actually average over the photon states. Well, the most naive possible way we can average over these photon states is just to take this wave function, take its modulus squared, and then integrate over all the photon modes to get rid of them. In other words, we trace out the photons. What do we get? Well, we then find, of course, that the diagonal matrix elements are not affected, but the off-diagonal matrix elements are modified by a factor here, which is just this trace over, sorry, there's something missing here. That should be a 2. There should be a superscript 2 here, I beg your pardon. So, but this is traced over the photons. And of course, this will be less than 1 in general. And in fact, if the coupling is strong enough, this average will reduce the off-diagonal matrix elements to 0. And this is what has been called decoherence, which, by the way, is an old subject. The first discussions of it were by Heisenberg in the 1930s. There were more extensive discussions in the 1950s. And by the time people really started to think about it and write papers where they used the word decoherence, actually it was already a very old subject. There are two remarks I want to make. First of all, you notice that this environment E, which is causing this decoherence and which is in effect performing a measurement, there's no reason why we have to talk about energy exchange between the photons and the electrons, although in fact in that case there will be some. The only question is whether or not there's phase information being communicated between the environment and the system. And the second is, and this is what I'm saying here, the key is that the two of them be correlated. That is to say, the state of the environment is conditional on the state of the system. Now, one of the things that I'm going to be doing in these lectures is asking, how does this work in real-world systems, particularly in systems that are of interest currently for quantum information processing? So that means we're going to go to an example. Whoops, sorry. And I'm going to discuss, I thought of this on last week when I was listening to the lecture of Jean Dalibard. I thought it would be interesting to take an example that's been studied here in Paris, which is the dynamics of vortices in Bose superfluids. So this is a real-world example. I'm going to be discussing something that goes on in experiments, which means that some of the theory is a bit messy. But it doesn't matter. You shouldn't care about the technical details. What you want to know about is the answer and also how we got there. So I will show you the theory, but I'm not going to discuss the details very much. So let's look at this. So vortices were discovered, they were suggested in 1950 by Onsager, and Feynman wrote a number of papers on the idea in the period from 1951 to 53. And in 1956, they were actually seen experimentally for the first time by Vinan in the UK. And so that means that there's an awful lot of experimental work has been done on them. And of course, I can't summarize that at all. What I want to do is just mention some experiments, which are kind of interesting. The first one, which is what I'm going to be talking about, is this experiment that was done here in Paris 9 years ago, where a Zeppelin-shaped cold gas was sliced into a whole bunch of essentially quasi-two-dimensional Bose systems. And the interesting thing now is that you can look at vortices in each one of them, in principle. Okay? And in fact, experiments were done on vortices in these essentially two-dimensional Bose condensates. And the question is, how do those vortices move inside the superfluid? And the advantage of looking at a two-dimensional system is that you don't have to worry about the fact that the vortex in 3 dimensions can fold and all over itself and get into what are called vortex tangles. The dynamics is much simpler in 2 dimensions because the vortex is just a point moving around. One can have one or more of them. Now, these vortices are definitely quantum mechanical objects. In fact, a very nice experiment that was done actually quite a long time ago now showed this. If you take a sample of helium-4 and you apply a strong electric field in it, then you can move electrons through the helium. They will very rapidly accelerate to a velocity, a critical velocity, and what they do then depends on what is the pressure in the system. If the pressure is low, they'll emit rotons. This is a beautiful example of the famous Landau criterion for superfluidity in certain kinds of superfluid. But if you raise the pressure, it turns out that the velocity required to emit rotons becomes too high, and the system nucleates vortex rings on the electrons. And this is it's very easy to see this because the vortex rings immediately grow, and so the electron stops moving. And so what you see is an exponential decay of the current down as the electron cloud moves, and which tells you the rate at which they nucleate. And then it was discovered that at high temperatures, they nucleate according to thermal activation, but at low temperatures, just a constant rate. This is the inverse temperature here, showing that, in fact, the nucleation mechanism was a tunneling mechanism, it was a quantum mechanism. And lots of experiments have been done on this since. And in fact, nowadays, people look at what's called quantum turbulence, in which vortices are nucleated at very low temperatures entirely via quantum tunneling. These are some experimental papers in that area. So all of this is showing you that we should be thinking about the vortex in a superfluid, not as a classical object, but as a quantum object. Unfortunately, the debate about what is the equation of motion for these objects has been conducted throughout almost all of history as though the vortices were entirely classical objects. And these are some of the papers on this. There are other papers in the superconducting literature by people like, for example, Bardeen, Nozière, Leggett, and so on. In fact, Leggett has written both on the Bose and the Fermi superfluids. So here are the forces that are supposed to act on the vortex when it's moving in the superfluid. Now remember, in the superfluid, one has to think of this naively in terms of a superfluid component and a normal component. Phenomenologically, this is the famous model of Landau. But remember, we can superpose these. In fact, Landau remarked that one should think about the superfluid and the normal components as being a superposition of 2 different kinds of motion for each part of the system. Now, the vortex is supposed to be moving through this like a classical object, according to these theories. And then in case there's going to be a superfluid Magnus force acting on it, which is proportional to the velocity of the vortex relative to the superfluid. So this is the vortex velocity minus the superfluid velocity in a cross product with the circulation. Okay? So this is just the standard Magnus force in hydrodynamics, but now applied to the vortex. The vortex is generating a rotating flow. And the same thing happens in a magnetic, by the way. I'm contrasting here magnetic vortices with superfluid vortices. Now, there has to be, of course, a drag force from the normal fluid. So this is the velocity of the vortex relative to the normal fluid. The normal fluid may be moving at a different velocity from the superfluid. We can imagine a wind of quasi-particles moving relative to the superfluid. Whoops. And this will cause a drag on the vortex. Same in a ferromagnet. But as Jordansky pointed out in 1965, there's another force. A force which looks like a Magnus force, but now it involves the velocity of the vortex relative to the normal fluid. And that's because quasi-particles moving on one side of the vortex, imagine the vortex is turning like this, will, as it were, be decelerated. One's going on the other side will be accelerated. So this is an example of this is rather like a Bernoulli force coming from the normal fluid acting on the vortex. You're all familiar with how it is that if you're traveling along in a train and another train comes by in the opposite direction, the two of them get pulled together. That's another example of the Bernoulli force. And then finally, this vortex is supposed to have an inertial mass. So this is a classical analysis of the dynamics of a vortex. We imagine the vortex has some coordinate. It's like a solid object moving through the superfluid, and these are the forces that are supposed to act on it. The problem is that nobody could agree on what these forces were. In fact, it was argued by Thales over a 20-year period that the Jordansky force did not even exist. And there have been a lot of arguments about the magnitude of these forces. There was also an argument which was eventually settled on whether or not this Magnus force term here was exact or not. And I think the agreement now is that it is exact, and one uses topological arguments to obtain that, which are best phrased in path integral languages. So, disagreement on most of the terms, except for the Magnus terms, and the second problem is that all of these theories treat the vortex as a classical object, and we know that that is in general not true, that at sufficiently low temperatures it will actually behave very much as a quantum mechanical object. So how do we do this properly? So I'm just going to describe mostly the results of a treatment which was fully quantum mechanical here. These are the references. But I want to give you an idea of what's going on here by discussing a much simpler problem first. This is the so-called quantum sine-Gordon model. So this is a very simple model. In fact, people often discuss it by imagining a long line of pendulums hanging, but there are springs connecting each pendulum to its neighbor. And now you see that there are two kinds of motion here. You can have the pendulums swinging through small oscillations, but we can also turn them over and produce a kink. So this graph here shows, as a function of the displacement along the line, the angle of these pendulums. And here, this is the kink. We basically turn it completely over. And this kink is something you can't get rid of unless you move it off to the end, or if it meets an anti-kink, and then the two annihilate each other. So this is a very simple example of what's called a soliton. And in fact, this is the equation of motion here. This is just the wave equation with here, if you like, the gravitational term acting on the kinks. Now, the kink solution has an exact form here, which I'm not going to discuss. This is just the picture of it. But we can ask, how does the kink, how does the soliton interact with small oscillations? That's also very easy to understand. The small oscillations, we just add them here. So this is the kink. And then we add a small oscillation to this, and we ask, what's the equation of motion for the small oscillation? Well, it's very interesting, because the small oscillation sees the kink as a potential well. So the small oscillation, just a wave moving along the line here, when it encounters the kink, it sees it as a potential well. And in fact, you can get bound state. If I now imagine transmitting waves from one end of this line to another, then they will, in general, notice this potential well. I should have drawn a picture of the potential well, but basically it's just a 1 minus s squared potential. And in fact, so the modes that we can have, we have a bound state here. So this is the center of the kink. This is one of the modes of the small oscillations. And then there are traveling waves, which when they travel through here, their amplitude goes down because they have to be orthogonal to this bound state. Okay? And you notice that the effect of Lagrangian for these small oscillations involves, well, this is just the traveling wave part of it. And then there's an interaction with this effective potential here, but you notice that it's quadratic in the field modes. That's important. It means that there is no linear coupling between these quasi-particles, these small oscillations, and the kink. So it's not like QED. In QED, you have a linear coupling between the electrons and the photons, a coupling which is proportional to the A or A cross, where these are the second quantization operators for photons. There is no such coupling here to a soliton. Okay? That's necessary because the soliton is a minimum action solution to the equations of motion. Okay, so now we go through the very complicated routine of this, doing basically the same thing I did here, but now for a two-dimensional vortex system. And it's a mess, so I'm not going to discuss the details. I'm just going to say that one can do it and that it's really a mess. These are interactions between the vortex here and pairs of phonons in the system, or pairs of density fluctuations. And the effective interaction matrix element is really horrible. It actually has singular properties in the low momentum limit. This because the vortex has a long range profile. But in the end, one can calculate what we were going to do before, which is the density matrix for the vortex, the reduced density matrix for the vortex. We start off with the density matrix for the entire system here, and then we perform a canonical transformation to single out the vortex coordinate, and then we write down the influence functional for this density matrix. And we do this, and it's really a mess. But the key is that we end up with equations of motion for two things now. Because I'm going to take the density matrix, which is a function of two variables, r and r prime, for the vortex, and I'm going to define a center of mass coordinate here, which is the sum of these, and a difference coordinate here, which here. Now the point is that this corresponds to the vortex center of mass, and this difference here corresponds to fluctuations, quantum fluctuations, because it's telling you about how far away the paths are from each other. Okay? Remember, the density matrix is defined over two paths. The center of mass coordinate is just basically how the center of the wave packet for the vortex coordinate, and this difference coordinate is telling you how far away the paths get from each other. It's essentially telling you about quantum fluctuations about that. And we can actually derive equations of motion for both of these coordinates, the quantum fluctuation coordinate and the center of mass coordinate. And they contain forces. But remember, the only reason this looks classical is we're talking about path integrals. We never actually quantize. We simply talk about paths. So these are the equations of motion for these paths. Okay? And they're very messy. But the key is that there's a difference between the high temperature behavior, the classical behavior, and the low temperature behavior, which is easily understandable if we Fourier transform in time. And then it looks very simple. In the frequency domain, this is the vortex coordinate, and this is the force on it. And this is what an electrical engineer would call an admittance matrix. It's a relationship between the force on the system and its time evolution. And in two dimensions, it's a matrix. For those of you who are familiar with the Hall effect, this is just exactly the kind of 2D conductivity matrix you would write down. It will contain diagonal elements which correspond to the straightforward longitudinal conductivity, and it has off-diagonal matrix elements which correspond to the Hall conductivity. And this is here, what I've written down here is in the classical domain, where we can write it in terms of these forces. And it has, well, an inertial term, a dissipation term on the diagonal, and then this off-diagonal part here is the analog of the Hall conductivity. And the key is, and by the way, this force here contains the Magnus force. The driving force contains the applied external force acting on the vortex plus the Magnus force. And the point is that in the quantum domain, all of these things change. And what I'm going to do to finish is show you a picture of how they change. It turns out that there are long-time tails which show up at low frequency. So this shows you what the longitudinal, the analog of this is just essentially the longitudinal dissipation acting on the vortex. What it looks like is a function of time. In other words, if I kick the vortex at some time, what will the resistance to the motion, longitudinal motion, look like as a function of time? You see there's a long time tail here. The same happens in the transverse. Moreover, in this equation of motion, just as you would always expect in something of Langevin nature, you have a fluctuation force on the right-hand side. So you can think of this as a quantum Langevin fluctuation force acting on the vortex coordinate. And at high temperatures, this is not important. It's just temperature noise. At low temperatures, it becomes a quantum noise. And it becomes extremely non-local in time. In other words, there are very long-time non-Markovian memory effects in this fluctuation, which is exactly what you would expect in a quantum system where the interactions are long range. And so you find that the behavior of the system changes completely in the low temperature regime. That is, the vortex dynamics must change completely. So this is showing you the diagonal part of this noise and the non-diagonal or transverse part of this noise. This is noise which, if you try and move the vortex in one direction, the noise will actually try and knock it sideways. And one can calculate all of these results, and you find the key point is that they're very non-local in time, which means they have very strong infrared effects. And one can summarize this, and this is my last slide, in this picture here. This is the characteristic frequency of motion of the vortex. Now, there are many different ways to move a vortex. You can, in the experiments that are done here in the lab of Jean Dalibard, they do it, I think, one of the main ways is just by rotating or applying a time-dependent force on the vortex at some frequency. So that would be that frequency. But there are other ways in which one can perturb a vortex. This is the temperature. The classical behavior is in this regime. This is where you get the classical equations of motion, which are sometimes called the Hall-Vinan-Jordansky equations. And they work here. This is what this theory shows. But then in the quantum regime, the equations are completely different. For example, one of the diffusion constants changes by a factor of 16, and so on. So these are big changes. And then there's a crossover regime between the quantum and the classical. And the interesting thing is that in the extreme quantum regime, you get what look like local equations of motion, but with completely different coefficients, plus this noise. In the classical regime, you have also local equations, and in the crossover region, they're completely non-local. It's not possible to write down what looks like a Newtonian equation. Okay. This means that there's a whole new regime to explore here. And the question is, how easy is it to get to it? Now, in talking with people who know about these experiments, for example, in Vancouver, I asked Kirk Madison, what ratios were attainable in experiments, and it seems as though it should be possible to get into this quantum regime. Actually, people working in turbulence think they can do the same, quantum turbulence, in very low temperatures in helium-4, but we'll see. So that's the end of my first real-world example. And as far as decoherence is concerned, what we see is that the effect of the phonons on the vortex dynamics is essentially to make it look completely classical at high temperatures. Basically, the old discussion where you just treated the vortex as some body, some object, classical object moving through the superfluid with drag forces and so on acting on it was right. And that's because of decoherence. On the other hand, if you go to low enough temperatures, it goes completely wrong. And I haven't shown you the results for the quantum fluctuations, that is the deviations of the vortex away from the classical path, but of course they become large in this quantum regime. And so what we're seeing here is that the simplest possible way to switch on and off decoherence is just using temperature. But we'll see that there are other ways of doing it which are much more intelligent. In fact, I will briefly mention biological systems where there's been a big discussion going on in the last few years about room temperature quantum coherence phenomena. So, thank you.